take you to practice quiz. This isn't displaying right. Let me close it out, open it back up. Alright, now it's displaying. Alright, practice quiz problem number 1. This was a homework problem. Looked like some people needed some assistance with this, so it's now a practice quiz problem. The volume of a cylinder, V, in terms of radius r and height h, is given by this formula. The cylinder has a height of 6 meters. Express the radius as a function of volume. Find the radius of the cylinder with volume 300 cubic meters. So before I have you work this, I'm going to show you a little bit about the, well, actually...
Can you expand your screen just a little bit, Robert? Is that possible? Because it's
okay.
Just maybe like a tiny bit.
Like this? Alright, but oh, you know what? I'm realizing something. This problem will go better if I do these first. So let me go these first. Number 2. State the formula for the circumference and area of a circle. So, don't look these up. See if you can remember them. If you can't remember them, take a wild guess and see if you're on the right track. Okay, 20 seconds more. Alright, so I drew a circle of radius 3. And if you did a circle of radius 3, and if you stretched a string from here all the way around the circle, it's certainly going to be longer than 6, because this distance 6 is called the diameter of a circle. And if you take that diameter of a circle, that won't even get you from here to here. Because from here to here, the shortest distance between these 2 points is 6. So this is a longer way to get there. And it will take you about 2/3 of the way. If you went that distance 6 from here to here, you'd get one of those 6's. And then if you did it again, from here across, you'd get about around here, another 6. And if you did it again, you'd get almost back to the beginning, a tiny bit short. And this doesn't work for just a circle of side radius 3. It doesn't matter what it is. If this was radius r, then this would be 2r, for the diameter. And then you take 2r, the radius, no matter what it is, it'll get you about 1/3 of the way around the circle, the diameter will. And then, so it doesn't really matter what size circle you have. You get almost around. You go 3 times around, you need 0.14 more. You need 2r times pi. 2r is the diameter times pi. But we usually don't see it that way. We usually see it 2 pi r. Put the pi second, 2 pi, and then r in that order. But I kind of think of it as this is the diameter, and how many diameters go around the circle? A little more than 3. That's diameter. Okay. And then the area of a circle. If we, let's go to a different color here. If I had this square that surrounds this. This square that surrounds my whole circle would be 1r across, because r is distance across here. So 2r. It would be 2r by 2r. And when you multiply it together, you get 4r squared. 4r squared is bigger than the area of the circle, because it's the area of the square that contains the circle. You need smaller than that, but not too much smaller. You need 3, but 3 isn't quite enough. 3.14, you need pi r squared. Alright, so those are the two formulas. Circumference of a circle, area of a circle. And notice, to help you remember them, there's only 3 different symbols, the same 3 symbols in both formulas. A 2 and a pi and an r. A 2 and a pi and an r. They're just rearranged differently. And if you had, let's say the units were inches, circumference would be in inches. And area would be in square inches. How many squares do you have? And inches squared comes out from squaring that unit. And this unit, the only one with a unit like inches, would be the r. And it gives you square units, gives you non-square units. So it makes sense that this is the one for circumference, this is the one for area. All right. Give me a little feedback on number 2 for circumference and area. Did you need this review? Did it add any insight? So a lot of people looks like they already had this. That's great. And alright. Find the circumference of a circle with radius 1. And a circle with radius 1 is called a unit circle. Let me give you a brief bit of time. "30 seconds more." So all we're going to do is take this 1 and plug it in here. So we're going to get circumference is 2 pi times the r, which is 1, which is 2 pi. Alright, this is going to be really important to us today. We're going to have to remember this. A circle of radius 1, called a special circle, called a unit circle, has a circumference of 2 pi. And because 2 pi is its circumference, 2 pi is going to have special meaning for us. We're going to be getting into angles today, and we're going to see 2 pi taking a very special role today. And now let's come back to this one. Okay, the volume of the cylinder. Let me give you a little bit of time. Like this. Okay, let me stop you here because I want to focus on this formula a little bit so that you have a little insight into this formula. What a cylinder looks like is like a Coke can. Okay, now the volume of a cylinder is the same as if we find the, we're going to go with the, now this cylinder down here is going to have a radius r, when I make it too small it complains, and a height h. Okay, and if we can find the area of the base of the cylinder, well, the area of the base is just the area of a circle, and the circle has radius r, and the formula for the area of a circle is area is equal to, we just had that, pi r squared. Two pi and r are the three ingredients, but we need to put them so that we get a square unit for area. Okay. Now, this is not only the area of the base, but it's also the volume, because it's how many squares are, like if you divided this up into rectangles and counted the rectangles, you would be getting pi r squared as the area, how many rectangles there are. But not only is that, but it's also the volume of the very first layer. Because if you take that and multiply it by a height of 1, right here, so the area of this times a height of 1, you'd have all these little ice cubes in here, but up to 1 layer. So if this was times 1, it's now the volume of the very bottom layer. And then how many different layers are you going to have? H layers. So if you take this pi r squared, and now it's not just a 1 but h layers, you get the volume. of the whole. And so that's a little insight into this formula here. Now, if a cylinder has a height of 6, so then we're going to have V equals pi r squared times 6, because 6 goes in for the h. Express the radius as a function of the volume. Now, what does it mean to express the radius as a function of the volume? What that really means is solve for r. So r is going to be alone on the left-hand side. This is the volume as a function of the radius and the height. So this is going to be the radius as a function. So it's going to be like r equals f of v. So the v is going to have things acting on it. Okay. So we just take this thing and we solve for v. So I'm going to divide both sides by 6 pi. And I'm going to get r squared. I'm going to move this to the other side. V over 6 pi. And then I'm going to square root both sides. Okay, and find the radius of a cylinder with volume 300 cubic. So that's the answer to the first part. The radius is this. And then the second part is we're going to plug in 300 in for the V. And then we're going to get R equals square root of 300 over 6 pi. And that's the answer to find the radius is right here with that volume. And then you might punch that out in the calculator and get an approximate answer as well. Alright. Give me a little feedback on number 62 from a private.
Yeah, it was kind of cool right there. It reminded me of the inverses when you're taking the R2 and then that equals the V over the 6-2 and it turns into a square root on the other side.
It has some similarity to inverses. The only thing that we didn't really do, though, is when you're doing an inverse function, you interchange.
Yeah, you didn't switch the signs or anything.
Yeah, you interchange the two variables, and we didn't do that. This is just changing its format. Changing the R, solving for R. Okay. So, a little bit of feedback here. And okay, write these two formulas. Don't look them up. Compound interest formula, continuously compounded interest formula. Seconds more. Alright, so the compound interest formula is a new amount is equal to the original principal 1 plus r over n. Because remember the interest rate, but you only get like maybe 1/4 of it if it's compounded quarterly. But you get it more often. Not just each year, but n like 4 times every year. So it's like this. And then continuously compounded interest formula starts out A equals P, and it's not going to have an n. because it's like we've taken n off to infinity, compounding an infinite number of times. And that produces e to the rt, pert, like this. Alright, so let me know, were you able to remember either or both of these formulas? Because we want to commit them to memory. If I could get feedback from everybody.
Yeah, I can get back into the screen, but no, I was not able to, Jordan.
Thank you. Okay, could I get feedback from everybody here? I got 1, 2, 3, 4, 5, 6 feedbacks. But we got 4, 7, 10, 11 of us here. Okay, good. And okay, write a recursive formula that comes up with this sequence, and a explicit formula, and an explicit formula for that. Looks like we have 2 more weeks of class after this week, and then we have a spring break. Okay, let me interrupt you here. You may have only gotten to the first one. If so, then I'm interrupting at the right time. The recursive, when you're giving a recursive formula, you always have to state what you're starting with. Sometimes you even have to state more than one. And then you're going to say something, how do I get the next one? Or the current one that I'm after, and it has to do with the one before. Now this is just the same as if you had gone like this, an plus 1, and put a sub n. As long as this one subscript is 1 smaller than that subscript. This will do exactly the same thing as that one will do. Right.
Thanks for showing this, Robert. I got the 13.4, but I was wondering about this, so thanks for showing.
Good. So how do I get from here to here? Well, I could add 6, but if I add 6 again, it won't get me to the next one. So what can I do consistently that'll get me to the next one? If I multiply by 3, and then I keep multiplying by 3. That's what I do. So that's all I have to do over here is 3 times the one that was the predecessor. Okay, so this is, we kind of think of this is the current one, and then use the previous one. Or if you think of it with the next formula, it's almost like, how do I get the next one? Well, you take 3 times the current one. So depending on how you want to word them. And this gives you the recursive formula. Right. Now, I'm going to give you a little more time.
There's one question. I'm sorry. With the subscript subtraction, that was one thing I wondered about. It's like n minus 1 or something like that. That was a question I had.
Okay, so this, for instance, if n is, like if we're trying to find 2, so n is 2, and we use this formula, this would tell us a sub 2 is equal to 3 times a sub, now 2 minus 1 is 1, and a sub 1 is this 3. So that would tell you that a sub 2 is 9, which is correct. And then you do it again with n equals 3 and so on. Okay? So it's just, this is a subscript 1 smaller than that. Okay, let me give you a little time with the explicit. Explicit formulas are generally harder to come up with than recursive formulas. Okay, 30 seconds more. And you don't have to do this, but what I tend to do is I make a structure for this. And n is 1, 2. And then here's the sequence. But what we're looking for is a relationship between n and a sub n. So we kind of want to have these like this. And so if there's any way I can rewrite these so that it includes an n in them, then I'm on my way. But this is 3 to the first power. This is 3. Notice I'm being able to use the n every time. Alright, so this tells me that a sub n, now in an explicit formula, I'm not allowed to use a on the right hand side, just the n. Well, there's always a base of 3, and then what is it raised to? Always the nth power. Alright, give me a little feedback on number 5.
Yeah, I got that. Thanks for showing that. That helped a lot.
Welcome. Okay, need more practice, good feedback. These take a little while to get, especially the explicit. It's kind of thinking in a little different way. Let's do it again. Give me, number 1, a recursive. For this, I'll give you a minute. 30 seconds more. Alright, so I can think of that I get from here to here by like adding 4. But that doesn't get me to the next one. So I try something different. Let's say I multiply by 3. Well, that works again. Multiply by 3. And then multiply by 3, that always works. So my recursive formula would be a1 equals to a sub n equals something with the one right before it. What do I do with the one right before it? I multiply by 3. And that would do it. There's my recursive formula. And then now do your explicit formula.
Like for the recursive, I had it, but it was different. It was the variables were in different places.
Okay. Thanks, Jordan. All right, 30 seconds more on the explicit formula. So I'm going to make my structure n a sub n 1, and this is 2, 6, 18, 54. Now I want to rewrite these so somehow I involve the ends. Alright, so this 6 is really 2 times 3 to the first. And this is 2 times 3 to the second. Because, you know, they had more and more 3's as you moved along. You kind of noticed that. And this one is 2 times 3 to the third. 3 to the third is 27. 27 times 2 is 54. And this one is 2 times 3. There's no 3's. 3 to the 0 power, which is 1. Right. So now I have an idea. A sub n, there's always a 2. There's always 3 to some power. Now, it'd be nice if the n was always showing up right here. It's not. But as the n moves up by 1, this moves up by 1. And there's always this relationship. This exponent on the 3 is always 1 less than the n. So there is an explicit formula like this. Now it's not the only way to get this formula. There's a lot of different ways I could have come up with this. This is one that I find kind of that works. And all right, give me a little feedback on part B.
I just have to practice the subscripting a little bit.
Okay.
But that's all.
let's go to number 6, 2 parts. Do each of those. Find, that's called factorial, 5 factorial. And I think there was a homework problem. You had to read about that in the section. And then this summation notation. Okay, 30 seconds more. Alright, so 5 factorial. The exclamation point, which means factorial, means start with that number, and where this means add them all up, the factorial shortcut for multiply them all up. Where this you count up from 3, 3, 4, 5. This you count down from 5. 5 times 4 times 3, and you keep going all the way till you get to 1. Times 2 times 1. And then I'll kind of group these together. That's 20 times 6, that's 120. So that's factorial. We find factorial, especially if you go on in math and do more, especially in statistics and probability. You see factorial show up a lot. In the world of computer science, you see that a lot. This summation notation. Start with k being 3 and substitute it in. So you get 6 minus 1. And then make k go up by 1. So k is now 4, and now you're going to get 8 minus 1. And then k is going to go up to 5, and that's going to be where you stop it. And when it's 5, you get 10 minus 1. So we got, what is this? 5 plus 7 plus 9, which is 12, plus 9, which is 21. And give me a little feedback on number 6, parts A and B.
Hi, Mr. Shankin.
Hi.
I'm confused on how you got 6 minus 1
Okay.
and like how you got that whole equation set up.
This 3 went in for the k. And 2 times 3 is, that's how I got the 6. And then the k becomes 4, and then 2 times 4 gives you the 8. Is that clear?
So you go through 5, 4, 3, 2, and 1?
You start with the bottom number.
Okay,
Is this
so
Sasha?
yeah.
Okay. Yeah, you start with the bottom number. You substitute k being 3 to start with. And then you plug it in. And that gets you here. And then you go k equal 4, plug it in, and that gets you this one. And then k equal 5, plug it in, that gets you this one over here.
Okay. Okay, I got it now.
Okay, all right, let me look at the feedback. Thanks for asking, Sasha, when you're confused. I'm sure you're not the only one who had a question. let's go. All right, we're done with practice quiz. And are there questions? Anybody have any questions from the homework or any other questions?
Yeah, tell Sasha one way I thought about that. I even wrote it like as a joke, is like the sigma's like the boss of the numbers, and he like orders them around, and
That's the boss.
he's like telling them like, you guys get in line and stuff like that. So yeah, my one question about the 5 on him is it matter if it's on the sigma's, I guess, head, or does it matter or does it matter if it's like on the side of him? It's the same thing.
Oh, right. Sometimes I get them to show up top and bottom. Where did I get that? Somewhere up here.
He's kind of sticking the 5 is kind of
here. See, I got it to go. It's just this software. It doesn't matter. And if it has room, it'll put them underneath and above. And otherwise, it sticks them kind of to the side. It doesn't matter.
I think it was kind of cool. He even had a number crown and stuff. It just, that letter is the king of the numbers.
That's the boss. All right. Anything else? Any other questions?
Homework 22 on 13.1.
13.1, number 22. All right, and that's on page 104. If I go to that, 22. And all right. Write an explicit formula for these. So I'm going to do n a sub n. There's 1, 2, 3, 4, 5 of these. And then I am looking for a relationship between the n's and these numbers. And now, oftentimes, like when I gave the practice quiz, I'd have you look for a recursive formula first. And that's kind of helpful to kind of just get the feel for this thing. I mean, is there something I can do to this one to get to the next one? What if I, like, I would add 6 maybe? But then adding 6 doesn't do it over here. But then add 12. And then add, no. Subtract 12. And then add 24. Ooh, these things are growing there. One time it's adding, next time it's subtracting. And then the next one, I would subtract. I have to subtract 14 and then 34 more, that makes 48. Ooh, and it alternates adding and subtracting, and it goes like bigger and bigger numbers that are being added in there. So now, if I multiply by a negative number to go from one to the next, that'll alternate it in sign, because every time you multiply by a negative, it changes the sign of the previous thing. Okay. And these things, how am I going to get to these? This looks kind of difficult here. I'm kind of feeling stumped on this. So if I was doing this in reality, I would probably have to write down a couple ideas and then take a break and say multiply, so the recursive formula, I'd make this little note, multiply by a negative number to get to the next. To the next item. Because then that would alternate in signs maybe. But I would think I would have to, pause and really think about this and come back to it, try it again in a while. So let's put that into practice. Let's take a break. We will start again. At 1:33 p.m. And before I take my break, does anybody need to talk with me about anything?
That one was driving me nuts too. I was like,
Yeah.
My brain felt like it was like, there was one just like that. I was like, oh my God.
Yeah, it's kind of doing that to me right now too. Like I'm going to have to pause and think about it and come back a couple times to this one. All right. Anybody else? No? Alright, we are going to start up again. And I have not been able to figure out the answer to number 22. So, when I get stumped, that makes this one special. So, if anybody wants a challenge, I'll give you extra credit. And you get a whole bunch of, and if you want to, you can explain it to the class. If not, you can just, send it to me and I can explain your answer. But I'll give you like 3 extra credit points I'll put on a homework. So instead of like getting 7 points for the assignment, you can get 10 points if you can come up with this answer. Plus, you'll become a star. And all right, now we had another question as well, but I need to go on to the next section. So the question was number 18 and 3.4, and if time permits, at the end of class today, we'll come back to that. But we need to move on, make sure that we get far enough in the new section. So 7.1, angles. And we're going to start with the question, and this is the second half of this course. The first half of this course was picking up some leftover topics from college algebra. We needed to review, like you see these topics, on the side here. We needed to review exponential functions, inverse functions, logarithmic functions. We needed something new, asymptotes. We needed to review domain and range. Something new is absolute value equations and inequalities. So a bunch of miscellaneous topics we needed to review and add a little bit to compound interest, so that we had continuously compounded interest. And sequences and series. Now, the second half of the course is totally different than the first half. It's going to be on trigonometry. And if you've had a little exposure to trigonometry, you might have an idea. What is trigonometry? And let me just ask anybody, does anybody have an idea of what trigonometry is about? Anybody want to open their mic and just take a guess? Trigonometry is about what?
Triangles and angles.
You're exactly on the right track. It's the study of angles, and we begin with angles in a right triangle. So both of the ideas that you said, where one angle, a right triangle is one angle is 90 degrees, and jobs that use trigonometry a lot are carpenters, surveyors, and navigators. Now, navigators can use, a smartphone now, so they don't really need it so much. Carpenters and surveyors, I've talked to people who've either been carpenters and work with them, and they say, oh yeah, they use trigonometry for angles quite a bit. And they said, generally speaking though, they don't have kind of what you're going to get in this portion. You're going to get some understanding of some bigger principles. And they said they don't understand any of those bigger principles. They just know that when they have this situation come up, they do this kind of computation, and it'll get them this result. So the carpenters usually don't have a big grasp of trigonometry, but they're using it quite regularly. All right, now we have this question. What is an angle? And this is a tricky question because it's so intuitive. Everybody kind of knows what an angle is. But how do you put it into words? So what I want you to do is go into your group chat and type something up. Just the first thing maybe that comes to mind. What's an angle? And we'll look at over what a few of the possibility, a few of the suggestions are for what is an angle. Don't look it up, just what you think it is. And of course, like always, if you can't think of anything, you have to write into your chat, I'm stuck, I can't think of anything. But make some kind of guess as to how would you define what an angle is. So type it up, but don't hit enter yet. Go ahead and hit enter. Everybody make sure you've typed in something into your group chat. All right, and group 1, what do you have? What are some of the possible suggestions for what's an angle?
I don't know, like it says. Oh, I'm sorry. Go ahead, Sasha.
No, you go ahead. It's fine.
Are you positive? Okay, I was thinking about like in terms of like when it talks about like 90-degree angle, 360-degree angle. Like when they take that measuring stick or whatever it is, and then figure out like the exact placement of something within a three-dimensional box, for instance. Like this goes in particular. I mean, that's what I was thinking, just in terms of like the different dimensions of a three-dimensional object. Like there's an angle that leads up to the corner, and I don't know how to define it, but yeah.
But you're giving examples of it, like 90 degrees, 360 degrees.
Yeah.
And what's a tool we might use to get?
I'm trying to think a level or something like that, isn't it? Or maybe it's not a level. I don't know what that is. It's some kind of thing like that. I mean, I'm trying to remember. I think they do it with like some kind of laser pointing device now or something. But I'm sorry about that, Sasha. I didn't know you were gonna. Yeah, I still feel bad that that thing.
Remember these kind of things that tells you what, and you'd read the angle numbers, and up here
it would
show 90 degrees, and over here it would show.
I've seen them. I've never used them. I thought they're.
Yeah, they call this a protractor.
I think I was a kid and I used to play with one. Pretend like G.I. Joe porters.
It might have a hole in it, right down here. Oops. Right down here, and in that hole, you'd put like the vertex of the angle that you're at. All right, so now, it's really hard to put it in words. What is an angle? But here it is. It's the amount of rotation, and I would have never thought of this. The amount of rotation needed to bring one ray in coincidence with another, means on top of the other. So angles have two rays coming out from a common point. We call that the vertex of the angle. And we have this being the initial side of the angle, the other one being the terminal side of the angle. The positive direction of any angle is counterclockwise. So a clock moves the other direction, counterclockwise. And the angle is a little bit different than the measure of the angle. But when we do the measure of angle A, we could shortcut that notation and say M of A for measure of angle A. And then we can shortcut shortcut that even more, and math is really big at making shortcuts, and they don't like to write very much. If we can write less, we do. And so we just put A, and A stands for the measure of angle A. Thus, the measure of angle A, which we call just A, is equal to 60 degrees, is our shortcut notation. All right. Now, all these notes, like if you're scrambling to try to take notes real fast, you can just, access all this in OneNotes later if I'm moving too quick for you.
Yeah, that was a question I had, Robert, is where is the OneNote section? Because I think it's been throwing me off. I've never really been able to find the exact section in there where we can bring it up. Is that just in the modules?
Okay, so it's in the announcements. Go to the announcements in Canvas and go down to the very first one.
Okay.
And it tells you about, downloading Microsoft Office and using OneNote, and then it gives you a link. You have to click on that link, and it'll bring up, and then you have access to all my notes.
Okay, that's going to make it a lot easier, make my life easier. Thank you so much.
You're welcome. All right, so standard position. This angle is what we call in standard position. Standard position means the vertex is at the origin, and let's come back up here. We call this the vertex. The point at which both rays start out at. Okay? Vertex is at the origin in an XY axis. And the initial side is on the positive x-axis. Then the angle is called in standard position. We prefer angles in standard position in many situations. Coterminal angles. Coterminal angles have the same initial and terminal sides. Now, that definition might seem like, oh, how in the world could I find two other angles that are coterminal with 40 degrees? So, that's a problem for you, and I want you to put your answer into your group chat. You have to look carefully at that definition of coterminal. Find at least one other, but hopefully two other angles that are coterminal with 40 degrees. Let me give you a quick minute. Go ahead and hit enter and talk it out in your group. All right, group 4. Any ideas here? So Maya, are you here? Or backup, Lily, are you here?
I am. I think we'll pass.
Pass? Okay. All right. Anybody have an idea? Another angle is coterminal with 40 degrees.
So one way you could figure it out, right, is you could subtract out something. I'm just taking like a wild guess there. If you look at it as an entire, like I don't know, and maybe I was thinking of some other deal right there where you could end up with like a formula of a circle or something like that, where you could take one part of it and subtract it from the whole 360 or something to find.
The whole 360 is the idea.
Okay.
To get another angle coterminal with 40, you'd have to start in the same place. Now, 40 degrees is a little less than 45, which is over here. You have to end up at the same place, but you could go an extra revolution. Instead of rotating just 40 degrees, you could go 360 degrees, plus another 40, and that's what you could get. So you could get 360 degrees plus 40 degrees, which is 400 degrees. That is coterminal with 40 degrees. It has the same initial and same terminal side. It's kind of like winding up a spring an extra time, and then, but you still want, so this isn't the same as 40 degrees, because if it was a spring, it'd be more wound up and have more energy. But it does have the same initial and terminal sides. And you could do that with any multiple of 360. You could take 720 degrees plus 40 degrees, 760 degrees. That's also coterminal with 40 degrees. All right, and this brings us back to complete revolution. A complete revolution back to the starting point is 360 degrees. And why did they decide to say that a complete revolution is 360? Why didn't they use like 100? Because, if it was 100 degrees, that's kind of like a number that's easier to work with. And, we're a base 10 system. It's, when we look at it historically, why did they decide to do it 360? It probably had to do with 365 days in a year. But they wanted a number that was easily divisible by 4 because, 90-degree angle, 1/4 of a complete revolution is really important and so on. So they picked a number that was kind of close to 365, but not exactly, and call it 360. And when they kind of visualize days in a year, you kind of think of the sun and the earth going completely around. Woo! The earth going completely around, making one complete revolution within 1 year. And so, divide it up, and it's like 1 degree is kind of like how much the earth moves in 1 day. Okay. And so, terminology, when we're in trigonometry with angles, is here's all these ideas. A right angle is 90 degrees. Acute angle is between 0 and 90. Obtuse is between 90 and 180. Straight angle is 180 degrees. Two angles, A and B, are complementary if they add up to 90 degrees. And they're supplementary if they add up to 180 degrees. Radian measure. This is the big topic for today. All right. So what we're going to do is we're going to say for one complete revolution, let me get the size of this just right. We replace 360 degrees with 2 pi. Now why 2 pi? Because remember in the practice quiz today, the circumference of a circle with radius 1 is 2 pi. Thus, the distance along the outside edge, or the length of the arc of a unit circle, is the same as the radian measure of an angle if the angle is placed at the center of a circle. So, for instance, let's look here. we take a general unit circle and we say, all right, we're going to always be starting as if the initial side were in standard position. And then we rotate. Positive direction is counterclockwise. Okay, and if we rotate up to 90 degrees, it's up here. And if we rotate all the way around, it's 360 degrees. So we call this 0 degrees. And then we call it, if we rotate it up to here, we'd call this 90 degrees. And 180 degrees, and so on. But all the way around would be 360. But what we're going to do is we're going to replace this 360 degrees with 2 pi. Now, what that means for us is if this radius r is equal to 1, then the circumference around this circle is also 2 pi. And they chose 2 pi as the measure for going all the way around instead of 360 degrees in radian measure, because that's equivalent to the length of the outside edge of the circle as you go around for if the radius was 1. Alright, now the more we get into trigonometry, the less and less you're going to see degrees. And keep going into calculus, we very rarely see degrees. We're doing radian measure almost all the time. Okay? Oftentimes an initial problem will be stated in degrees because that's what most of the world is familiar with. But then we'll convert it to radians and do all our computations in radians, and we might convert back to degrees at the very end to report the answer back to the public because they don't know what radians are. Okay. So notice, if going all the way around, if that much rotation is, instead of calling it 360 degrees, instead we call it 2 pi radians. Then going halfway around is half of 360 degrees, 180. It would be half of 2 pi, so it would be pi. And then if we went half of that, well, half of 180 degrees is up here, 90 degrees. Half of pi is, instead of writing 1/2 pi, the convention is pi over 2. And then, if we went half of 90 degrees, it's a 45 degree angle, well, that would be half of pi over 2, which would be 1/4 pi, but we write it as pi over 4. All right. So what we're going to do is, we're going to be working with radians so much, we want to get these things memorized and get really familiar with the unit circle with all these different fractions of pi. So if this is 1 pi, or 180 degrees, this is going around from 180 degrees to then another half, or another 90 degrees would be 270 degrees. This would be pi plus 1/2 of a pi to give you 1.5 pi down here. But instead of calling it 1.5 pi, we call it 3 pi over 2. And the same thing, if you went 1 pi, so halfway around the circle, plus 1/4 of the pi from here to here, you'd get 1.25 pi. But we call it 5 pi over 4. So we get all these different values, and we got to get familiar with these fractions of pi, and then be starting to use radian measure pretty much all the time. All right, so notice the fractions of pi. Working with radians becomes much easier when the fractions are very similar, very familiar. So, quick question. Which fraction is larger and why? 3/4 versus 2/3. So, see if you can come up with an answer and a brief explanation and type it into your group chat. Which fraction is larger and why? 3/4, 2/3. Go ahead and hit enter in your group chat. Okay. Group 2. What's your answer for this? Which is larger and why?
Oh, we said that 3/4 is larger because it's equivalent to 75%, and 2/3 is equivalent to about 66%.
75% and 66 2/3%. And we could also just use a calculator. If you punch 3 divided by 4 in your calculator, you get 0.75, and you get this in your calculator, it's 0.666, and it goes forever. So we put a bar over it. Okay. And we can also look at it in lots of other ways too. If I was looking at a pizza, I'd much rather eat 3 out of 4 pieces of pizza rather than 2 out of 3 pieces of pizza, because the one part that I didn't eat is a bigger part on the 2/3. 1/3 of a pizza is bigger than 1/4. Lots of different ways to look at this. All right, so as quickly as you can, arrange these in order from smallest to largest. I'll give you a minute. Right. Okay, so let me pull them out from smallest to largest. I'm thinking the smallest one is here, 1/6. So I've used that up. And then the next smallest is be 1/4. So divide a pizza into 6 pieces and take one of the pieces. That's the smallest. Divide it into 6 pieces, take one of the 4, and that will be the next. And then similarly 1/3. And then 1/2. And then what's going to come next? 2/3, because it's missing a third piece, and then 1 whole piece, and then 1 1/3, which is the same as 4/3. And then, now if it was 12/6, it would be 2, so that's a little bit smaller. 2. If we're quick in doing this kind of task, we'll get a lot better at doing radian fractions of pi very quickly. So let's go here. On the interior of the circle, we're going to label each angle in degrees. Now, in your homework for 7.1, there's a small worksheet that just has these instructions. It has 2 of these unit circles. Unit means the radius is 1, and it has these directions on it. And so you're going to be asked to do this twice. And you know, if you have a printer, you can print it out, or you could just write it on paper and then, you know, take a picture of like normal homework. All right. So the idea is label each angle. Like this is 0 degrees. And this is 90 degrees. And then on the exterior, label in radians. Now, 0 is the same as 0 radians. You don't have to put rad after it. I just did for the very first one. And then 0 is also 360 degrees, which is also 2 pi radians. And if this is 2 pi, this is 180, which is pi, halfway around. And then this would have to be pi over 2. Now, this one right here, let me just note, this is halfway going from 0 to 90 is right here. This is 1/3 of the way going from here to here, and then from here to here is 2/3, and then 3/3 of the way up. All right, so with this in mind, I want you to fill in on the inside the degrees, and on the outside with the radians, the portions of the fractions. And I'm going to give you a couple minutes to get ahead of me, and then I'm going to do that as well. But see how far you can get before I start doing it. Okay, I'm going to blow this up bigger so I have an easier time writing this. And I'm going to put the angles halfway from here to here is 45 degrees. 1/3 of the way to 90 is 30 degrees. 2/3 of the way is 60. So double this angle to get to this. And then if I did these over here, this is 90 plus another 30, 120 degrees. This is 90 plus 45, 135 degrees. This is 130 degrees, 120 degrees plus another 30 degrees, 150 degrees. So notice from here to here you add 30, you add 30 again, you add 30 again, like this. Now, I just did the upper half. I'm going to fill the outsides now with the radian measure. If this is all the way around is 2 pi, halfway around is pi. Half of that is pi over 2. Half of that is pi over 4.
Okay, that's what I was confused about. I even put it in my group chat, and I feel real stupid. I thought pi was 360. Pi is 180. Pi is normally considered 180.
That's right. 2 pi
Okay,
is 360 degrees.
yeah, I just would assume.
1 pi is 180. That's right.
I was thinking that there was some like you can think of it like a whole pie or something, but no, that's not gonna.
Right.
It's not gonna work,
Doesn't
man.
look like it's 2 pieces of pie here, but
Yeah. Okay, so it's half is 180. Okay, cool.
yes. And so then, if we are going from here up to here, it's pi over 2. From here up to here is 1/3 of pi over 2. But what's 1/3? 1/3 of 90 degrees is 30 degrees. What's 1/3 of pi over 2? Well, you multiply. It's 1/6 of a pi. But instead of 1/6, we write pi over 6. Now, this is pi over 6. And we could write this as 2 pi over 6. And this is 3 pi over 6. 4 pi over 6. 5 pi over 6. 6 pi over 6. But instead we reduce all these fractions. 1 pi over 6, 2 pi over 6, but that reduces to pi over 3. 3 pi over 6, so I'm going up by 30 degrees every time. 30, 60, 90, 120, 150, 180. But I'm thinking in pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, but that reduces to 2 pi over 3. 5 pi over 6, that doesn't reduce. 6 pi over 6 reduces to pi. Alright, in a similar fashion, we could go by multiples of 45. 45, 90, 135, 180. We'll do it pi over 4. Pi over 4, it's 1 pi over 4, 2 pi over 4, but that reduces to pi over 2. 3 pi over 4, and that doesn't reduce. 4 pi over 4, which is pi. And then we can go around to the second half of the circle. We add 1 pi over 6, and we get 6 pi over 6 plus 1 pi over 6 is 7 pi over 6. And then we add another pi over 6, which is another 30 degrees, and we get 8 pi over 6. But 8 pi over 6 reduces to 4 pi over 3. That's how we really write that one. And then this one is 1 whole pi plus a half of a pi. That's 1.5 pi, but we write it as 3 pi over 2. And then we're going to come over here. We're going to take, well, what is this one when we get right to here? That's 1, let me make it a little smaller here. It's pi over 4, 1/4 smaller than going all the way around. If we went all the way around in fourths, that would be 8 pi over 4. 8 pi over 4 is the same as 2 pi, but it's in fourths. And if we come back 1/4, this would be 7 pi over 4. So getting used to all these fractions and being able to write them all in, it's easy to do this with degrees, because you add 30 degrees, each time. And then if we add 45 degrees, this becomes 225. Add 45, you get to here. Add 45 to that, you get 315 degrees. But what are these things going to be in terms of radian measure? It's going to be, so this is 1 pi, and this is plus 1 more pi over 4. So think of this as 4 pi over 4 plus 1 pi over 4, 5 pi over 4. And think of this was pi over 3 up, and this is going to be 6 pi over 3 is the same as 2 pi, but come back 1 pi over 3, so this is 5 pi over 3. And if you went up pi over 6, think of this one down here as going all the way around the circle, which is 12 pi over 6. That's the same as 2 pi, but then come back 1 pi over 6, so it's 11 pi over 6. And now, we've got the last thing to do really quick here, converting units. And let me show you, to convert 3 feet to inches, what we do is we multiply by a conversion factor. We say, what unit do I want to get rid of? Feet. What unit do I want to replace it with? Inches. Which one's bigger? Take one of the bigger one, 12 of the smaller, so that they're equal. Now what happens with the units is they will cancel out. And then you get 36 inches. Now, we don't often convert 3 feet to 36 inches this way. We just say, oh, you just multiply by 12. But when the conversion gets hard, this is the way you do it. So if I was doing 14 feet, and I was converting it to yards, I might accidentally multiply by 3 instead of dividing by 3. This method guarantees that I do it right. Feet is what I want to get rid of. Yards is my new unit. 1 yard is bigger. I need 3 feet to equal 1 yard. So then, when I multiply these together, I get 14 thirds. These cancel out. Yards. Which is the same as what? 4 2/3 yards. Alright, now same strategy is used to convert to radians and degrees. We take 38 degrees, and we're going to multiply. We need to get rid of the degrees. And we need to change it to radians. Now, going once around the circle, you can do the whole thing if you want. 360 degrees is the same as 2 pi radians. Alright. Now, the textbook will tell you this way. It'll say, instead of doing that, they'll say multiply by the conversion factor of pi over 180. Now, how did they get pi over 180? Well, they just reduced this. And so this is radians, and this is degrees. But if you try to memorize the conversion factor is pi over 180, and then you'll get it backwards on the other one. But this method of thinking will never leave you. It's really easy to remember this. So then all you do is punch this out into your calculator. The degrees cancel out, and then you're going to get 38 over 180. And you can reduce that or punch it into your calculator. Pi. And then it's in radians. And so the last one, 2.3 radians. We need to convert that So we need to get rid of radians. We need to make it become degrees. I can do 360 and 2 pi, or I can do 180 and pi. As long as these two are equivalent. And then radians cancel out. And then you just punch this out in your calculator. 2.3 times 180. 414 degrees. So you can convert from one unit to the other very quickly. And so the homework is 7.1. We'll stop here. Any questions? Sorry I went a little over time today.
Oh, it's Thursday. Okay, so 7.1 is just due at a spot check.
Yes. 7.1. The spot check is due on Tuesday.
Okay,
All right. Y'all take care and have a great weekend.
yeah, take it easy, Robert. It's nice to have someone.
Yeah.
Bye. Thank you.